Fluorescent lights are known to be relatively sensitive to voltage dips. This means that they have the potential to flicker, dim noticeably, or even turn off completely if the voltage experiences a significant drop below their designed operating range. However, this susceptibility is not uniform across all fluorescent lights, as it largely depends on the specific type of ballast used and the overall design of the lighting fixture itself. For instance, fluorescent lights that incorporate electronic ballasts tend to be more resilient and less prone to being affected by voltage dips when compared to those that utilize the older, more traditional magnetic ballasts. Similarly, compact fluorescent lamps, also known as CFL, come equipped with built-in electronic ballasts, which inherently makes them less susceptible to the negative impacts of voltage dips. When a large motor, like those commonly found in HVAC compressors, initiates its startup sequence, it can induce a voltage dip within the electrical system it is connected to. The magnitude of this voltage dip and its duration are determined by several factors, including the physical size of the motor, the amount of current it draws during its start-up phase, and the overall impedance of the electrical system. To mitigate the potential disruption caused by voltage dips, it is generally recommended to avoid connecting fluorescent lights and high-current motors, such as those used in HVAC compressors, on the same electrical panel whenever feasible. The voltage dip that occurs when a motor starts can disrupt the normal operation of fluorescent lights, leading to the issues previously mentioned, like flickering or dimming. In scenarios where it is not possible to place these loads on separate electrical panels, it becomes important to isolate them electrically as much as possible. This isolation can be achieved through the use of devices such as isolation transformers or surge suppressors. Isolation transformers work by providing a physical electrical barrier between the two loads, which effectively prevents the voltage dip from affecting the fluorescent lights. Surge suppressors, on the other hand, act by absorbing the voltage dip, protecting the fluorescent lights from potential damage. It is important to acknowledge that even when loads are distributed across different electrical panels, they still might be connected to the same distribution panel. In such cases, it becomes crucial to ensure that the distribution panel is appropriately sized and capable of handling the combined load of all connected devices, and that it is equipped with adequate overcurrent protection mechanisms. In addition to these considerations, the overall condition and age of the electrical system can play a significant role in determining the susceptibility of fluorescent lights to voltage dips. Older systems may be more prone to experiencing voltage fluctuations, which can exacerbate the impact on fluorescent lights. Furthermore, the physical proximity of the fluorescent lights to the motor can also influence their susceptibility. Lights that are located closer to the motor will generally experience a more severe voltage dip compared to those that are farther away. Given the complexities involved, it is highly recommended to consult with a qualified electrician. They can thoroughly assess the specific situation, taking into account all relevant factors, and determine the most appropriate measures to protect fluorescent lights from voltage dips caused by motor starting. Firstly, consider the ballast type in your fluorescent lights. Electronic ballasts are generally more resistant to voltage dips than magnetic ballasts. If possible, upgrading to electronic ballasts can help to mitigate the problem. Secondly, compact fluorescent lamps, CFLs, are less susceptible to voltage dips because they have built-in electronic ballasts. Switching to CFL might be a viable option in certain situations. Thirdly, when a large motor starts, it draws a significant amount of current, causing a voltage dip in the electrical system. The magnitude and duration of the voltage dip depend on the size of the motor, the starting current, and the system impedance. Fourthly, it is generally recommended to avoid circuiting fluorescent lights and high-current motors, such as HVAC compressors, from the same panel. The voltage dip caused by the motor starting can disrupt the operation of the fluorescent lights. Fifthly, if the loads cannot be circuited on different panels, isolate them electrically as much as possible. Isolation transformers can provide electrical isolation between the two loads, preventing the voltage dip from affecting the fluorescent lights. Sixthly, surge suppressors can help absorb voltage dips, protecting fluorescent lights from damage. However, they may not completely eliminate the problem. Seventhly, even if the loads are separated into different panels, they might still be connected to the same distribution panel. Ensure that the distribution panel can handle the combined load and has adequate overcurrent protection. Eighthly, the age and condition of the electrical system can also affect the susceptibility of fluorescent lights to voltage dips. Older systems might be more prone to voltage fluctuations. Ninthly, the proximity of the fluorescent lights to the motor can impact susceptibility. Lights closer to the motor will experience a more severe voltage dip. Tenthly, consult with a qualified electrician to assess the specific situation and determine the appropriate measures to protect fluorescent lights from voltage dips caused by motor starting. The electrician can evaluate the electrical system, measure voltage drops during motor starting, and recommend solutions tailored to the specific needs. When dealing with electrical systems, voltage dips, and sensitive equipment like fluorescent lights, understanding the underlying principles and potential solutions is crucial. A voltage dip, also known as a voltage sag, is a short duration reduction in voltage. It's a common power quality problem that can affect sensitive electronic equipment. Voltage dips are typically caused by the starting of large electrical loads, such as motors, or by faults in the electrical system. When a large motor starts, it draws a significant amount of current, which can cause a temporary voltage drop in the electrical system. The severity of the voltage dip depends on several factors, including the size of the motor, the impedance of the electrical system, and the capacity of the power source. Fluorescent lights, particularly those with magnetic ballasts, are sensitive to voltage dips. When the voltage drops below a certain level, the lights can flicker, dim, or even turn off. This can be annoying and disruptive, and it can also shorten the lifespan of the lights. Electronic ballasts are generally more resistant to voltage dips than magnetic ballasts. They can maintain a more stable light output even when the voltage fluctuates. However, even electronic ballasts can be affected by severe voltage dips. Several strategies can be employed to mitigate the impact of voltage dips on fluorescent lights. The most effective approach is to avoid circuiting fluorescent lights and large motors on the same electrical panel. This helps to isolate the lights from the voltage dips caused by the motor starting. If it's not possible to separate the loads onto different panels, other measures can be taken to isolate them electrically. Isolation transformers provide a physical barrier between the two circuits, preventing the voltage dip from propagating to the fluorescent lights. Surge suppressors can also help to protect fluorescent lights from voltage dips by absorbing the excess energy. Another important consideration is the capacity and condition of the electrical system. An older or overloaded electrical system is more likely to experience voltage dips. Upgrading the electrical system can help to improve its stability and reduce the severity of voltage dips. The proximity of the fluorescent lights to the motor can also affect their susceptibility to voltage dips. Lights that are located closer to the motor will experience a more severe voltage drop. Moving the lights further away from the motor can help to reduce the impact of voltage dips. A qualified electrician can assess the specific situation and recommend the most appropriate solutions for mitigating voltage dips. They can evaluate the electrical system, measure voltage drops during motor starting, and provide tailored recommendations. Understanding the NEC National Electrical Code is also important when dealing with electrical installations. The NEC provides guidelines for safe and effective electrical installations, including requirements for overcurrent protection, grounding, and wiring methods. It is important to adhere to the NEC when installing or modifying electrical systems to ensure safety and prevent electrical hazards. Here's a breakdown of some relevant NEC articles related to voltage drop and motor starting. Firstly, NEC Article 210.19. A1 requires that branch circuit conductors must have sufficient capacity to carry the calculated load. This includes accounting for motor starting currents, which can be significantly higher than the motor's running current. Secondly, NEC Article 215.2. A1 is similar to 210.19. A1 but applies to feeder conductors. Feeders must be sized to carry the calculated load, including motor starting current. Thirdly, NEC Article 430 covers motors, motor circuits, and controllers. This article provides detailed requirements for motor protection, overcurrent protection, and disconnecting means. Fourthly, NEC Article 430.52 specifies the maximum overcurrent protection for motor circuits. This protection is intended to protect the motor and circuit conductors from overloads and short circuits. Fifthly, NEC Article 430.22 addresses the ampacity of motor circuit conductors. The conductors must have an ampacity of not less than 125% of the motor's full load current rating. Sixthly, NEC Article 430.24 covers the sizing of conductors supplying several motors. The conductors must have an ampacity equal to the sum of the full load currents of all motors, plus 25% of the highest rated motor in the group. Seventhly, NEC Article 310.15 provides guidelines for determining the ampacity of conductors based on their size, insulation type, and ambient temperature. The NEC does not explicitly specify a maximum voltage drop for branch circuits or feeders. However, Informational Note Number 1 to NEC 210.19 A1 and Informational Note Number 1 to NEC 215.2 A1 recommend that the voltage drop on branch circuits should not exceed 3% at the furthest outlet, and the voltage drop on feeders should not exceed 3%. The combined voltage drop on both feeders and branch circuits should not exceed 5%. These are recommendations, not mandatory requirements, but they are widely accepted as good engineering practice. When calculating voltage drop, it's important to consider the length of the conductors, their size, the current they will carry, and the power factor of the load. Several online voltage drop calculators can help with these calculations. There are also several strategies that can be used to mitigate voltage drop in electrical systems. These include increasing the size of the conductors, shortening the length of the conductors, and using transformers to step up the voltage. It's also important to ensure that all electrical connections are tight and clean to minimize resistance. Large 8-track units are often powered by three-phase power, such as 208 volts or 480 volts. When dealing with three-phase power, it's important to understand the different voltage levels and wiring configurations. The most common three-phase configurations are Y and delta. In a Y system, there is a neutral conductor, and the voltage from each phase to neutral is the phase voltage. The voltage between any two phases is the line-to-line voltage, which is equal to the phase voltage multiplied by the square root of 3, which is approximately 1.732. In a delta system, there is no neutral conductor, and the voltage between any two phases is the line-to-line voltage. The NEC provides detailed requirements for grounding electrical systems. Grounding is essential for safety and helps to prevent electrical shock. The grounding system provides a low impedance path for fault current to flow back to the source, which allows the overcurrent protection devices to trip and clear the fault. Grounding electrodes, such as ground rods or ground plates, must be installed to provide a connection to earth. The grounding electrode conductor must be properly sized and connected to the grounding electrode in the electrical system. Bonding is also an important part of the grounding system. Bonding is the process of connecting all non-current carrying metal parts of the electrical system together to create a low impedance path for fault current. This helps to ensure that all metal parts are at the same potential, which reduces the risk of electrical shock. Metal raceways, enclosures, and equipment must be bonded together using bonding jumpers or other approved methods. Overcurrent protection devices, such as circuit breakers and fuses, are essential for protecting electrical systems from overloads and short circuits. These devices are designed to interrupt the flow of current when it exceeds a safe level, preventing damage to equipment and reducing the risk of fire. Circuit breakers are reusable devices that can be reset after they trip. Fuses are one-time devices that must be replaced after they blow. The overcurrent protection devices must be properly sized to protect the conductors and equipment they serve. The NEC provides detailed requirements for sizing overcurrent protection devices. Short circuit current rating, also known as interrupting rating, is the maximum short circuit current that an electrical component can safely interrupt. It's important to select components with a short circuit current rating that is equal to or greater than the available fault current at the point of installation. Available fault current is the amount of current that would flow in a short-circuit condition. This current can be very high, and it's important to protect electrical systems from the damaging effects of short-circuit currents. A short-circuit study can be performed to determine the available fault current at various points in the electrical system. This study can help to ensure that the selected components have adequate short-circuit current ratings. Harmonic distortion is a form of electrical pollution that can affect the performance of electrical equipment. Harmonics are currents or voltages that are integer multiples of the fundamental frequency. Nonlinear loads, such as electronic ballasts and variable frequency drives, can generate harmonics. Harmonic distortion can cause overheating of equipment, increased energy losses, and interference with communication systems. Harmonic filters can be used to reduce harmonic distortion in electrical systems. These filters are designed to block or divert harmonic currents, preventing them from propagating throughout the system. Power factor is a measure of how effective the electrical power is being used. It's the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolts amperes. A power factor of 1.0 indicates that all of the power being supplied is being used effectively. A power factor of less than 1.0 indicates that some of the power is being wasted. Low power factor can cause increased energy losses, reduced equipment capacity, and voltage drop. Power factor correction capacitors can be used to improve power factor in electrical systems. These capacitors supply reactive power, which reduces the amount of reactive power that must be supplied by the utility. Load calculations are an important part of electrical system design. These calculations are used to determine the amount of electrical power that will be required to serve a particular load. Load calculations must take into account all of the connected loads, including lighting, receptacles, appliances, and motors. The NEC provides detailed guidelines for performing load calculations. These guidelines specify the demand factors that can be used to reduce the calculated load based on the assumption that not all loads will be operating at the same time. Voltage regulation is the ability of an electrical system to maintain a stable voltage under varying load conditions. Good voltage regulation is essential for ensuring the proper operation of electrical equipment. Poor voltage regulation can cause equipment to malfunction or fail prematurely. Several factors can affect voltage regulation, including the impedance of the electrical system, the size of the conductors, and the capacity of the power source. Transformers are used to step up or step down voltage levels in electrical systems. They are also used to provide isolation between different circuits. Transformers consist of two or more windings that are electrically isolated but magnetically coupled. When alternating current flows through one winding, it creates a magnetic field that induces a voltage in the other winding. The ratio of the number of turns in the two windings determines the voltage transformation ratio. Electrical safety is of paramount importance when working with electrical systems. It's essential to follow all safety precautions and to use appropriate personal protective equipment (PPE). Always de-energize electrical circuits before working on them. Use a voltage tester to verify that the circuit is de-energized. Wear insulated gloves and safety glasses. Never work on electrical equipment in wet or damp conditions. If you are not qualified to work on electrical systems, hire a qualified electrician. Electrical accidents can be serious or fatal. Take the necessary precautions to protect yourself and others.